Welcome to Talk 3. This one is particularly relevant if you work in oncology, cardiology, or any area where you're tracking time to an event, death, relapse, discharge, resolution. Kaplan-Meier curves are everywhere in veterinary literature, and they look intuitive, but there are several important things hiding beneath the surface that most readers miss. By the end of this talk, you'll know how to extract median survival times, understand censoring, interpret the hazard ratio, and spot when a KM curve is misleading. Roadmap for today. We'll spend the most time on the curve itself, reading it, interpreting it, and understanding the hazard ratio. I'll also flag the most common pitfalls, narrow curves that look reliable but have few animals left, and crossing curves that break the hazard ratio assumption. Let's start with what the curve is actually showing. The Meyer curve is a graphical estimate of the survival function over time. The y-axis starts at 1, meaning 100% of the animals are alive and event-free at the beginning. Every time an event happens, say a dog dies, the curve steps down. The size of each step depends on how many animals were still at risk at that moment. The flat sections are intervals where nothing happened. Everyone was still alive or event-free. Unlike some other methods, KM doesn't assume that the risk is constant over time. Maybe most deaths happen in the first 3 months and then the surviving animals stabilize. KM captures that. This is why it's so widely used. Little vertical tick marks on the curve, those are censored observations, and understanding them is crucial. A censored animal is one where we just don't know what ultimately happened. Maybe the owner moved and was lost to follow-up. Maybe the study ended before that animal reached the endpoint. We know they survived at least until they were censored, but we don't know what happened after. The KM method accounts for censoring by removing censored animals from the risk set going forward. It's statistically valid, but only if censoring is random. If sicker animals are more likely to drop out, the curve will look artificially optimistic. This is called informative censoring, and it's a red flag. When you see lots of censoring early in a study, pause and ask, why are animals leaving early? Reading median survival time is simple once you know the trick. Draw an imaginary line across the graph at y equals 0.5. Where that horizontal line intersects the survival curve, drop straight down to the x-axis. That's your median survival time. This tells you half the animals in that group experienced the event by this point in time. Why median and not mean? Because survival data is almost always skewed. A few animals with very long survival times can pull the mean up dramatically and make a treatment look better than it is. The median is more robust. And if the curve never reaches zero point 0.5 by the end of the study, that means more than half the animals were still alive or event-free at last follow-up. That's actually great news. The median survival time is not yet reached. Rank test gives you a p-value for the overall difference between two curves. It's testing whether the curves are the same or different. But the hazard ratio gives you the actual magnitude. It's the ratio of event rates between groups at any point in time. Think of it like this. If the HR is 0.6, it means at any given moment in the study, animals in the treatment group are experiencing events at 60% of the rate of the control group. That's a 40% reduction in the rate of dying or relapsing. When you read a KM paper, look for both. The log rank p-value, is there a difference? And the hazard ratio with confidence interval. How big is the difference and are we confident in it? Here's a trap many clinicians fall into, the right end of a KM curve. The curve may look perfectly stable and flat at month 24, but look down at the numbers at risk table below. If only 4 animals are still being tracked at that time point, that flat line means almost nothing statistically. One event could send it plummeting. Always read the numbers at risk table. It gives you the denominator for the curve. The curve is most reliable in the early months when many animals are being observed, and least reliable at the tail end. Some journals now require this table. If you don't see it, it's worth being skeptical about late time interpretations. This is an advanced but important concept, and it's one that catches even experienced readers. The hazard ratio assumes that the relative risk between the two groups stays constant over the entire follow-up period. This is called the proportional hazards assumption, but sometimes the curves cross, meaning one treatment is better early and the other is better late. Think about immunotherapy in cancer. There might be early deaths from treatment toxicity, so the control group looks better initially. But at 12 months, the immunotherapy patients who responded are doing very well, and the curves cross. If you just look at the overall HR and P value, you might get a non-significant result, missing the fact that immunotherapy has a very real late survival advantage. The practical lesson: always look at the KM curves themselves, not just the statistics. Do the curves cross? If they do, a single HR is not telling the whole story. Here's a realistic clinical scenario. You're reviewing a study of 120 cats comparing radioiodine treatment to medical management for hyperthyroidism-associated cardiomyopathy. The median survival for radioiodine is 38 months versus 22 months for medical management. The log rank P is 0.008, statistically significant. The hazard ratio is 0.52, meaning radioiodine is associated with roughly half the rate of death at any time point. For the client consultation, this represents a meaningful survival advantage for radioiodine, 16 additional months of median survival, and the result is statistically significant with a confidence interval that doesn't cross 1. This is clinically meaningful information. But the caution: by 36 months, there are only 9 cats in the radioiodine group and 4 in the medical management group. The curves at that time point are based on very few animals. That portion of the curve is unreliable. Don't overinterpret what happens after month 30. The practical message: radioiodine appears to offer a meaningful survival advantage in this population, supported by a reasonable sample size in the earlier time periods. The data beyond 30 months should be interpreted with caution. The key takeaway is this: always look at where the numbers at risk get small. That's where you stop trusting the curve. Summarize: KM curves are elegant and informative, but they require careful reading. Steps down mean events. Tick marks mean censoring. Read the median by crossing at y equals 0.5. Interpret the hazard ratio as a relative rate ratio and check the confidence interval. And always read the numbers at risk table. The tail of the curve is often the least reliable part. In Talk 4, we switch gears to vaccine trials. How is vaccine efficacy calculated? What's the difference between relative and absolute risk reduction? What's the number needed to treat, and why does it matter for real-world recommendations? See you there.